professor in information theory here at Télécom Paris and in the communications and electronics department. I joined the faculty in 2009, right after obtaining my PhD from ETH Zurich and after a short postdoc at UC San Diego. The goal of my ERC project is to derive the fundamental limits of sensing systems, distributed estimation and detection systems. Sensing systems are present and of crucial importance nowadays and even more tomorrow. In fact, the Internet of Things is really just a network of sensors. And future 6G standard, mobile cellular standard, is supposed to provide anytime and anywhere sensing capabilities to all terminals in the network. In wireless, we have a huge problem of bandwidth. So bandwidth is saturated. And nowadays systems, so they use certain bandwidth for communication. So they send signal for communication and certain bandwidth for radar. So you send the signal and then you analyze what is backscattered. And so the new paradigm is actually to send a single waveform that codes or transmit the data, and then you use the backscattered for radar purposes. And this, of course, will save bandwidth, so will improve performance. So we can use more bandwidth for both tasks. And also, again, reduce hardware costs because we only have a single system. And so wireless integrated sensing and communication is especially important for industrial robots and autonomous vehicles because their communication is wireless and they need to detect obstacles and communicate to each other. Wireless communication theory, then signal processing, physics, and also instrumentation sciences, they all contribute very fundamentally and crucially to these systems. So I think what we can do in information theory, we can build or set a theoretical basis, and then we can derive fundamental limits of these systems. That's actually important for three things. So the fundamental limits, which means the optimal performance, sets a benchmark. So we know how far our current systems are for optimal. And also it gives insights on how to improve current systems. And finally, knowing this optimal performance of different systems allow you to choose which one you want to use for which application. So this is a contribution of information theory to the field. The new proof techniques that derived in the last few years is actually called, so it's under the name of change of measure proof techniques. And so the rough idea is that you take your problem or the system you want to analyze, you simplify it slightly so that you can solve it, and then you show that actually you didn't change the system too much, so the solution to the new system is still going to apply for the old system. So it's just like in abstract terms. Similar proof techniques had been proposed. So what I think is new in our proof technique is that we have managed to come up with a very simple proof technique. And this is good because then it allows many people to use it. And on the other side, with simple techniques, we can attack very complex systems. So even like multi-objective systems, like this integrated sensing and comm, where we have two objectives and need good sensing performance and good data rates or reliability of communication. Or also like sensor systems with lots of detection centers. So this is all things we can attack with our new proof techniques. We have new masters, like for example the MICAS masters and also the multimedia networking masters. And these masters attract very good students who often are interested in pursuing a PhD. So this is one way we can get in touch with potential candidates. We can even test them on our during the lectures or on projects. And then I think also like ERC Paris helps us with its reputation.